Hi, my name is Shahroz Ahmad and in this video I'm going to discuss about the gravitational fields. So let's start off with the definition first. Gravitational field. So gravitational field, it is a region or space where a mass experiences gravitational force. So that region or space is called a gravitational field. Alright, so let's suppose we have Earth. This is Earth, and the influence of the gravitational field is up till here. And whenever there is some mass that is placed within this gravitational field, this region or space is basically called the gravitational field. And let's suppose there is a mass that has been placed within this region. So some sort of force will be exerted on this mass, and that force will attract the mass towards its center. So this region is called the gravitational field, and that force that is being exerted onto this mass is called the gravitational force. Alright, so this is about the gravitational field. Now let's discuss about the gravitational force. So gravitational force. So in order to explain the gravitational force, I have to explain it by using the Newton's law of gravitation. So the Newton's law of gravitation says that the force of attraction between two masses, the force of attraction between two masses is directly proportional to their product and inversely proportional to the square of distance between them. Inversely proportional to the square of distance between them. So let me just complete it. Distance between them. So now let's consider two masses. This is mass m1. This is the center of this mass m1, and there's another mass. This is, let me just draw it a bigger mass. So this is m2, and this is the center of this mass. Now the distance between them is, let's suppose that distance is r. Now there will be some gravitational pull between these two masses, and that gravitational pull will be considered as the gravitational force. Now that gravitational force will be directly proportional to the product of their masses. Means the bigger the mass, the bigger the gravitational pull would be. And it also depends on the distance between them. If the masses are closer, the pull will be bigger, and if they are away from each other, there will be less gravitational force between the two masses. And this law applies on all the masses in this universe. So let me just write it in the equation form. So F is directly proportional to the product of two masses, and force is inversely proportional to the square of distance between them. Now if I combine it, so it will become F is directly proportional to m1 m2 over r square, or when I write that into the equation form, it will become F equals to F will become equal to G m1 m2 over r square, where m1 and m2 are the masses, r is the distance between the centers of two masses, and G is the gravitational constant. The value of this gravitational constant is 6.67 times 10 to the power of negative 11. Alright, so this is it for the gravitational force, and this is the formula for the gravitational force. F equals to G m1 m2 over r square. Now we'll discuss about the gravitational field strength. So gravitational field strength. So gravitational field strength is basically, we represent it with small g. Let me just write down the definition first, then I'll write down the formula. So it is the force exerted on a mass that is placed in a gravitational field. So force per unit mass placed in a gravitational field. So that is called the gravitational field strength. So we represent the gravitational field strength with small g, and that is equals to capital F over m, whereas this capital F is the gravitational force, and this m is the mass that is being exerted onto the mass that is being placed in the gravitational field. So let's suppose this is Earth, and the influence of this Earth or the gravitational field is in this region, and there's a mass placed within this region. Now the amount of force that is being exerted onto this mass, the force of attraction basically that is being exerted onto this mass, will be the gravitational field strength of this point. If this mass come closer to the Earth, let's suppose this mass will come over here, the gravitational field strength will increase. If the mass will go away, the gravitational field strength will decrease. So this is how it works. Now, as I have told you that G is equal to F over m, where G is the gravitational field strength. So as we know that force is equals to G m1 m2 over r square. So I'll replace F with G m1 m2 over r square divided by m. So I'll consider that between these two, m1 and m2, one mass is m2. So I'll cancel it out. So my G will become equal to G m over r square. So in this case, this m will be considered as the mass of this Earth, due to which the force is being exerted onto the mass. So this m will be considered as the mass of Earth, and r is the distance between the point mass, between this mass or this mass from the center of the Earth, and g is the gravitational constant, that is 6.67 times 10 to the power of negative 11. And the unit for this g will be newtons per kilogram. So this will be the unit for the gravitational field strength. Okay, now the next phenomena that we have to discuss is about the gravitational potential. So let me just erase it all. Gravitational potential. Alright, so before that, let me just draw a figure. So let's suppose this is Earth. The influence of Earth or the gravitational field of Earth is up till here. There's a mass that is placed on the surface of the Earth. At this point, when the mass is placed on the surface of the Earth, the gravitational potential energy of this mass is 0. Now what we do is we do some work on this mass, and we move this mass up to some height. Okay, now when we have moved this mass from this position to this one, it means that we have done some work done onto this mass, which has resulted the increase in gravitational potential energy of this mass. Okay, so when we will move this mass from the surface up to some height, we will say that the work done is done on the mass, and that work done is positive. That work done is positive. Why? Because we have done some work done and the object has gained some gravitational potential energy because it has attained some certain height. Now let's come over to the concept of gravitational potential. So from here you can see that if we move the object away from the surface, away from the Earth, it means the work done is positive. Now let's suppose that there is a mass that is placed outside the gravitational field. This is the mass. We do some work done onto this mass and bring that mass within the gravitational field over here. So in this case, because we are moving towards the earth, so our work done will be negative. One thing, and this gives us the definition for the gravitational potential. So gravitational potential is basically the amount of work done on an object in order to bring it from infinity into the gravitational field. This mass is at infinity for the earth, because the gravitational field of earth has no influence onto this mass. So this mass is considered to be at infinity. So I'll write down the definition of the gravitational potential, that the work done on a mass in bringing it from infinity to a point in the gravitational field. So that work done is considered to be the gravitational potential of that particular point. So if we bring the mass from infinity to this point, then this will be considered as the work done that has been done onto this mass will be considered as the gravitational potential of this point. If we do more work done and bring the mass over here, then obviously our gravitational potential will be more. If we bring the mass right on the over here, then our gravitational potential will be less. So we represent the gravitational potential with this symbol that is called phi, phi, and this work done is basically equal to negative gm over r. Alright, so a negative sign represents that the work done has been done against the gravity, so that's why it's negative. And g is the gravitational constant, m is the mass of the earth, and r is the distance of the mass from the center of the earth. So this is the formula for the gravitational potential, and the unit for the gravitational potential is joule per kilogram. This is the unit for the gravitational potential. Now after gravitational potential, let's move on to the gravitational potential energy. That is quite simple concept, but we have to write the gravitational potential energy in terms of the Newton's law of gravitation. So gravitational potential energy. Alright, so this is Earth. There's a mass placed on the Earth. We move the mass to some certain height. So we say that we have done some work done onto this mass, because I have moved this mass from the surface to some point in the field. So let's suppose this is the distance r. This is distance r. So now let's find out how much will be the gravitational potential energy. So as we know that the gravitational potential energy is equal to mgh. Now from the gravitational field, this is the gravitational field strength, and this h is basically r, the height, and m is this mass. Alright, so what I'll do is I'll write g equals to gm over r square. So I'll just substitute this value into this g. So my gravitational potential energy will become equal to g m h, that is r divided by r square. This will get cancelled, and my gravitational potential energy will become equal to gmm over r, where capital M is the mass of the earth, small m is the mass of the object, and r is the distance between the centers of these two objects, and g is the gravitational constant. So this is the gravitational potential energy. This is the formula that we use for the gravitational potential energy. Okay, so now for all right, now I'm just gonna write down all the formulas for the force, field strength, gravitational potential, and gravitational potential energy together over here. So the formula for the gravitational force is G mm over r square. The unit is Newton. For the gravitational field strength, the formula is Gm over r square. The unit is Newton per kilogram. For the gravitational potential, the formula is negative Gm over r. The formula is Joule per kilogram. And for the gravitational potential energy, the formula in terms of Newton's law of gravitation will be Gmm over r, and its unit will be Joule. So this is it for the gravitational fields topic. Now we'll do some exam related example question. Alright, so here I have an exam related question that says the moon can be assumed to be a uniform sphere of radius r. Write an equation for the mean density of the moon in terms of r, g and small g. This capital G is the gravitational constant and this small g is the gravitational field strength. So as we know that the density is equals to mass over volume. Now we have to find out the mass and volume separately for the moon, and we'll insert into this formula and we'll get the density. So let's first of all see the volume. So volume is equals to 4/3 pi r cube, because I'll consider the moon to be a sphere. So this is the volume. Now for the mass, I will take the equation for the gravitational field strength, that is G equals to Gm over r square, and from here I'll get m equals to g r square over capital G. So this is the mass and this is the volume. Now I'll insert this mass and volume into this equation for the density, and I'll get the mean density for my answer. So that would be equal to g r square over g divided by v, that is 4/3 pi r cube. So it will become g r square over capital G times this will become 3/4 pi r cube. This square will get cancelled with this one, and our final answer will become equal to 3g over 4 pi capital G r. So this will be the mean density of. Alright, so now in the part B it says the moon has a radius of 1700 kilometer and a mean density of this much. Show that the gravitational field strength on the moon is about this much. So we have to find out the gravitational field strength. So I'll use this same formula where I'll say that D is equal to 3g over 4 pi capital G r. I have been given r, I have been given the density, and I have to make G as my subject first of all. So I'll make G as my subject, so it will become 3g will become equal to 4 pi g r t, and G will become equal to 4 pi g r t divided by 3. Alright, so I have to write the radius in meters, and I have to write the density in kilogram per meter cube. So this one will become 1700 times 10 to the power of 3, and in order to convert the density into kilogram per centimeter cube, I have to divide it by 1000. So I have to divide this density by 1000, and I have to times it by 1 million, because I want to convert this gram into kilogram and per centimeter cube into per meter cube. So my density will be like this, 3.34 divided by 1000, and per centimeter cube, because it's already in the denominator, and in order to go from the centimeter cube to the meter cube, I have to divide it by 1 million. So it'll be like this. So this 1 million will come into the numerator. So my density will become 3.34 times 1 million divided by 1000. So in this way the density will become 3340 kilogram per meter cube. I'll insert that density over here and work out my value of G. So it's like 4 pi times 6.67 times 10 to the power of negative 11 times 1700 times 10 to the power of 3 times my density, that is 3340, and everything divided by 3. So let me just put that into the calculator and see what I will get. Alright, so I got exactly, where do I write? I'll write it over here. So I got the value of G exactly to be, it is like 1.586, so I'll round it off, so it will become 1.6 Newton per kilogram. So the most important thing in this part was to convert the units into the distance and the density into the standard units. So we had to convert the radius into meters, and we had to convert the density into kilogram per meter cube. So the conversion was critical. Now let's move on to part C. Alright, so in this part it says the planet B has mass m, radius r, planet Q has radius 4r. The values of the gravitational field strength at the surfaces of P and Q are the same. Determine the mass of Q in terms of m. So we have two planets. One planet has a mass, let's suppose this planet is planet P and this planet is planet Q. The mass of this planet is m and the mass of this planet is unknown. The radius of this planet P is r and the radius of this planet is 4r. So I'll just draw it a bigger planet. So the radius of this planet is 4r. So this is planet Q and we have to find out the mass. But the one information that we have been given is about the gravitational field strengths. So the gravitational field strength on the surfaces of both the planets are same. So the gravitational field strength on planet P is G equals to Gm over capital R square, and on this planet that would be G equals to G, and we do not know the m, so I'll just say Gx over 4r whole square. Now as these two are equal, so I'll put them equal to each other, so it'll be like Gm over r square is equal to Gx over 16 r square, where x is the mass of this planet Q. Now I'll make x as my subject, so this G will get cancelled, this r square will get cancelled, so x will become equal to 16 m. So the mass of the bigger planet is 6 times the mass of planet P. Alright, so now let's read out this part. It says figure 1 shows how the gravitational field strength above the surface of planet P varies with distance from its center. The values of the gravitational field strength at the surfaces of P and another planet R are the same. Draw on the diagram the variation of gravitational field strength above the surface of planet R with a radius 3r over the range shown. Alright, okay, so planet P has a radius of r, but planet R has a radius of 3r. So we have to find out the gravitational field strength of either of them. So what happens is we have not been given any information about their masses, so it says that the gravitational field strength on the surfaces will be same. So remember that the gravitational field strength starts to decrease from the surface. From the center to the surface there is no change in the gravitational field strength. Since the radius of planet P is r, so that's why the gravitational field strength will start to drop from r, and since the radius of planet R is 3r, so it will start to drop off from here. because at this point we can see that the radius is, the distance from the center is 3r. So it will start to drop from here and the curve will be same as of this one. So it will be like this. It will go right in parallel to the other graph. So it will go like that. So this is how the graph of gravitational field strength for the planet R will look like. So I hope you got the concept, and this is it for this section of the gravitational fields. Thank you.